Good morning. My name is Manikant. Now I am going to say about stress intensity factor for typical geometries. This course is about aerospace structures. First of all, what is stress intensity factor? Stress intensity factor describes the stress state at a crack tip. Is related to the rate of crack growth and is used to establish the failure criteria due to the fracture. The magnitude of K depends upon the specimen geometry, the size and the location of crack or notch, and the magnitude and the distribution of loads on the material. And it can be written as K is equal to sigma root over pi A times f of A by W, where f of A by W is a specimen geometry. Dependent function of crack length is A, and the W is specimen width, and sigma is the applied stress. Stress intensity factor for typical geometries. Let us go through the typical geometries. So see this. This is an infinite body, and there is a crack at bit of a length of 2a, and due to this geometry, on as we discussed in the brief before the equation for the stress intensity factor, that is K is equal to sigma root over pi A times f of A W. So this is the one. The Ki is equal to sigma root over pi A, where f of A by W is equal to 1. So this is a stress intensity factor. Now let us go through this one. This is a finite width one. This is an infinite body, but this is a infinite but a finite width one. So width is constant for this. So for this, the stress intensity factor is given as this one. Ki is equal to root over sec pi A by W times sigma root over pi A. So here we can clearly say that the geometry, the specimen geometry, f of A by W is given as root over sec of pi A by W. So this is the next body. It's a semi-infinite body. So this is an edge crack. So just now we have gone to the center cracks. Now it's an edge crack. So of length A. So this is the stress intensity factor for this. That is Ki is equal to 1.12 times sigma root over pi A. So it clearly says that the geometry, the specimen geometry is 1.12. Now here, the center crack in a finite width strip. So this is a center crack of a finite width strip of length 2a. So this is a table which is allocated for A by W, that is geometry 0, and H by W, where H is this one and W is a width. So A is varying, right? So that's the thing. So for this, some vectors, and the formula goes with Ki is equal to normally F times the A by W times sigma times the root over pi A. So edge crack in a beam of a width B subject to bending. So normally it's a beam having an edge crack. So see this. For this, the stress intensity factor is given as f of A by W times sigma times the root of pi A, where sigma is equal to 6m by bw square. And this is a table for this A by W and f of A by W. Let us go to the thin sections. There's a plate stresses. Double split beam. This is a double splitting beam. So for this, the stress intensity factor is equal to 2 times the root over 3 times PA by C power of 3 by 2. And next, the typical geometry is circumferently notched round. So it's a notched round with some cracks here, and here. So of a diameter D and a minimum minimum perfect diameter is small d, and the pressure is P. So Ki for this one stress intensity factor is equal to 0.92 p root over d by pi d square for 1.2 less than or equal to d by d less than 2.1. This is a limit for this one, and this is the stress intensity factor for this circumferentially notched rod. Compact tension specimen CST. So this is a crack here for the compact one. So for this, it is given as Ki is equal to y times p root over pi by b by root over w. So this is a compact tension specimen. And let us go to the next one. This single-edged notched. The single-edge notched bend, that is SENB, of thickness B. So this is the one. And for this, the thickness, the stress intensity factor is equal to y times 4p by root pi by b by root w, and the cracking emanating hole in an infinite body. So this is a cracking emanating hole. So it says that the hole is going to increase for this. So for that one, the stress intensity factor is equal to F times A by R times sigma root over pi by A. So pi A. And these are the different geometrical things that have brought to the stress intensity factor for different geometries. And thank you.